Welcome to this episode of Robert's Creative Chronicles. So today, we'll be discussing about Kirchhoff's laws. There are two Kirchhoff's laws. There's Kirchhoff's current law and there's Kirchhoff's voltage law. That is KCL and KVL respectively. So Kirchhoff's current law, that's the KCL, states that in any electrical network, the algebraic sum of the currents meeting at a point or junction is zero. That is, the total current entering a junction is equal to the total current leaving that junction. Now consider the case of a network shown in the figure below. So here is the network. So from this network, you can see that the current I1 enters this junction A, I2 is leaving the junction, I3 also leaves the junction, I4 is entering the junction, and I5 is leaving the junction. When applying KCL, you can use your convention. You can use any convention. You can use a convention that any current that enters the junction will be assigned to a positive sign, and the one that leaves the junction will be given it a negative sign. Or you can do it in the other way. You can say any current that enters the junction will give it a negative sign, and anyone that leaves the junction will give it a positive sign. But you must use it consistently from beginning to end. In this convention, any current that enters this junction, I am assigning a positive sign to it. Then anyone that leaves it, I'm assigning a negative sign to it. So, but you can use it in the other way. You can use the other reverse of this, provided that you maintain it from beginning to end in all the currents. So I1 enters this junction. Positive I1 plus minus I2 is leaving this junction is negative. Then I3 also is leaving this junction A, which is negative also. I4 is entering is positive. I5 is leaving is negative, equals to 0. So this is the KCL. We have successfully applied KCL. So you can rearrange it. So you can rearrange this. You see I1 plus I4 minus this minus I2 minus I3 minus I5 equals to 0. Then if you take this all to the other side, it will be I1 plus I4 equals to I2 plus I3 plus I5. Meaning, so I1 and I4 are the only two currents that enters this junction. So I1 and I4 are the only two currents that enters this junction. Then I2, I3, and I5 are all leaving the junction. So this is also telling us that the sum of incoming currents is equal to the sum of outgoing currents. So this is all about Kirchhoff's current law. That's KCL. So now the second Kirchhoff's law, which is Kirchhoff's voltage law, KVL, states that in any electrical network, the algebraic sum of the products of currents and resistances in each of the conductors in any closed path or mesh in a network plus the algebraic sum of the EMFs in that path is 0. That is the algebraic sum of product of currents and resistances plus the algebraic sum of the EMFs is 0 around the mesh. It should be noted that algebraic sum is the sum which takes into account the polarities of the voltage drops. So this algebraic sum, you must put signs. Some will be positive, some will be negative, depending on the voltage drop and the direction of motion around the mesh. Now consider the closed path A, B, C, D, A in the figure below. This is the closed path. It's a mesh. Now our direction of travel will be clockwise direction. As we travel around the mesh in the clockwise direction, different voltage drops will have the following signs. Now, when we are moving in clockwise direction, you know, current moves from higher to lower potential. That, in other words, current moves from positive to negative potential. So, all the currents you are seeing here, I1, I2, I3, I4, any direction they are moving to is at a lower potential than the direction they are coming from. Now I1 is moving from A to B. That means A is at a higher potential than B. Since I2 is moving from B to C, B is at a higher potential than C. I3 is moving from D to C. That means D here is at a higher potential than C. And I4 is moving from D to A. That means at D is at a higher potential than A. So here, the higher potential is usually giving positive sign, and the lower potential is giving a negative sign. So we are moving in clockwise direction. Now these two voltages, the longer terminal is giving a positive sign, so it's a positive potential. This longer line that I drew is always this longer. These are two terminals of this voltage. The positive one is usually longer than the negative one. So these two voltages have two terminals, positive and negative. Current will move from this positive and enters the negative. So current usually comes from the positive terminal and enters the negative terminal. So when we are moving in this clockwise direction, the voltage across here, that is given by Ohm's law I1 R1, is negative. That is, there's a fall in potential because when we are moving in direction of I1 in clockwise direction, so I1 is moving from higher to lower potential, and the final potential this will be is negative. So since we are moving in direction of this I1 and we are moving in clockwise direction, which is in the same direction as this I1, so since this is moving from point A to B, that means, and we are moving in clockwise direction, that means the final potential we'll meet is negative. So we are always taking the sign that this voltage will take is the final potential. We are not going to take the first potential. We are only considering the last one that we'll meet before we leave that current, or before we leave the branch. So now, since current moves from higher to lower potential, that means here will be positive, here will be negative. That means we will move, as we are moving, we will pass positive potential. The last one will come across negative potential. So since we are coming across the negative potential, that's the sign, the last one that will come across the sign, that's the sign of that one that will assign the voltage. In the same way, the second one, I2 R2. I2 is moving from a higher to lower potential, and we are following it from that higher to lower potential. So we are going to make use of the lower potential, which is the last one we come across, which is negative. So I2 R2 is negative. There's a fall in potential from higher to lower. Then I3 R3 is positive, because do you know why? There's a rise in potential, because in this one we are not moving in the same direction as the current. The I3 current is moving from a higher potential here to a lower potential here. So here will be positive, here will be negative. We will pass negative potential here. The last one we're going to meet here is a positive potential. That is positive. That's why we're going to make use of the positive one. So as I said before, it's the last one that we pass that we're going to make use of, not the first one. Since current is moving, the actual current I3 is moving from a higher to lower potential. Here will be negative to represent lower potential. Then here will be positive to represent higher potential. So we are going to pass the negative potential and meet the positive potential at the end. So we are going to make use of positive. That is, there's a rise in potential. Then I4R4 is negative, fall in potential, because we are moving in the same direction as this current, which moves from higher to lower potential. So it will be positive, negative. So we'll take negative, which is the end thing we are going to meet, which is the last potential we are going to come across. So it's negative, that is fall in potential. Now E2, the second voltage. When we are moving in clockwise direction, we will pass positive potential. The last one we are going to meet is the negative. So from positive to negative, there's a fall in potential. So we are going to make use of the last one we are going to come across, which is negative. So E2 is negative, fall in potential. Then E1 is positive. Why? Because when we come here, we are moving from negative to positive. That is from lower to higher potential. So we are going to make use of the last one we came across, which is positive. So E1 is positive, rise in potential. So one thing I want you to know in analyzing this circuit. One thing that will really help you when you are doing mesh analysis or when you are applying KVL, I want you to know that current always flows from higher to lower potential. If you know this, you'll be able to analyze any circuit using mesh analysis or KVL. Current always flows from higher to lower potential. From higher to lower potential. If you see a current moving in any direction, the direction it was coming from was at a higher potential than the direction it was going. That's all I want you to know. And if your direction of travel is the same as the direction of current, that means you are moving from higher to lower potential. You are following the current in its direction. But if you are moving against that direction, that means you are moving from lower to higher potential. So these are the three things I want you to take note of when applying KVL. So using Kirchhoff's voltage law, that's KVL we get, then you add everything. This negative, you assign negative I1 R1, negative I2 R2, positive I3 R3, negative I4 R4, negative E2, then positive I1. So you assign the respective signs after you have analyzed it. Then the algebraic sum is equal to 0. Then you can multiply 2 by negative. Then you move these 2 to the other side. Or rearrange it anyhow. You can also leave it like the same thing. So this is how you apply KVL to a circuit. You do this, you apply this KVL when doing, you use this KVL very well when you are doing mesh analysis. That of KCL, you apply it very well when you are doing node analysis. So you need these two Kirchhoff's laws. They are very important in mesh and nodal analysis in electrical engineering. So that's all. I hope you understood this episode. If you have any question, feel free to contact me using my WhatsApp or email written in the description below, or you can write them in the comment section. Thank you for watching. Please don't forget to like, share and subscribe to my channel, and hit the notification bell to get notified as soon as I drop a new video. Thanks.